Welcome back to the deep dive. Throughout this series, we've really embarked on quite a fascinating journey, haven't we? Moving beyond Transformer to explore what's next in sequence and language modeling.
We certainly have.
We've meticulously dissected the foundational limitations of the Transformer, that powerhouse AI architecture everyone hears about, driving so many large language models today.
Right, the quadratic scaling issue, the fixed context.
Exactly. And from there, we traced the really remarkable evolution of state space models, or SSMs, started with their theoretical roots, like HIPU, solving that long-term memory puzzle.
Well, online learning, yeah, a critical piece.
And an S4 showing how to make those ideas practical, scalable, all the way up to the very efficient Mamba models. We've even ventured into some pretty advanced territory like cross-architectural distillation with frameworks like a Mohawk.
Which is all about getting different model types to learn from each other, even if they're built completely differently.
Right. And we explored the truly revolutionary potential of HNets, which, they promise to fundamentally change how AI processes information by maybe, just maybe, ending the need for tokenization altogether.
Indeed, this whole series has really been an in-depth look at how the field is pushing beyond these, established paradigms, challenging some core assumptions that have, driven AI development for quite a while now.
So for this concluding deep dive, what's our mission? How do we tie all these threads together?
Well, the mission is synthesis, really, bringing it all together. We need to revisit the fundamental trade-offs, between these different architectural philosophies. Why does one work better here, another there?
Right.
Then we'll dig into the synergistic power of hybrid approaches, models that cleverly combine the strengths of these diverse architectures.
Makes sense.
We also, I think, really need to acknowledge the significant engineering hurdles. These dynamic hierarchical models aren't easy to build.
Right, the practical side.
But crucially, emphasize that these challenges are surmountable. We've seen this before with other complex AI systems. And then finally, we'll cast an eye toward the exciting future. Truly integrated AI systems learning directly from raw data, building abstractions, much like we do.
That sounds like a monumental task.
Yeah.
And absolutely essential to bring everything together. So, okay, what does this all mean for the big picture? How do these seemingly different advancements connect? Let's unpack this by maybe starting with those core distinctions again,
Yes.
SSMs versus the Transformer, reaffirming fundamental architectural trade-offs, SSMs versus Transformers. One of the most, I find, compelling ways to really get a handle on the fundamental differences between Transformers and SSMs is through this analogy, this intuitive comparison of how they actually operate.
Yeah, and what's really fascinating is how clearly their underlying mechanics, their computational processes, line up with these concepts. So when you think about Transformers, right, with their self-attention mechanism.
The core innovation.
Exactly. They operate very much like, highly sophisticated databases, their internal state. It's basically an explicit cache storing pretty much every single element of its processing history.
Every token, every interaction.
Every single one. Each new observation, each input token is treated like an important item to be meticulously filed away. Why? For perfect, explicit future reference.
Okay.
So when the transformer needs to generate something new or process the next piece of information, it essentially scans this entire ever-growing cache. It queries all those past entries to figure out the current context.
Which is incredibly powerful for tasks needing perfect recall.
Absolutely. But, and this is the kicker, it also means they have this fundamental hard limit on context length. That cache size and the computation needed to scan it, it grows quadratically with the sequence length.
Right, the n-squared problem we discussed early on. That database analogy is so clear strength and perfect recall, but this hard memory limit. So if transformers are databases, what about SSMs? How does that brain-like processing contrast?
Well, by contrast, state space models, SSMs, they're much more akin to, biological brains. They have finite-sized memories, yes, but they aren't static caches.
Oh.
They're dynamic, constantly active systems. They process new inputs, generate outputs in a continuous online streaming fashion, always maintaining this compressed, ever-evolving representation of all past history.
So not a perfect itemized list.
Exactly.
Right.
Their state is more like a dense, sometimes fuzzy summary, which means SSMs don't excel at perfect rote memorization, like, trying to recall someone's phone number perfectly after hearing it once or memorizing the whole phone book.
Like humans, our memory is more associative, right? Summary-based.
Precisely. It's not a perfect data dump. But critically, and this is where the brain analogy really hits home, SSMs hypothetically maintain an infinitely long memory. It's continuously evolving, maybe a bit fuzzy, but it doesn't just hit a hard wall.
Unlike the Transformers' fixed context window.
Exactly. That stands in stark contrast. And this intuitive difference helps explain a lot of the empirical behaviors we've consistently seen as these models scale up. B, strengths and weaknesses unpacked.
You've brilliantly set up Transformers as this database. Let's delve into that a bit more. When is reaching for that kind of processing power the absolute best move? What kind of data or specific tasks really play to the Transformers' strengths?
Well, when we look at where Transformers truly shine, it's almost always in situations where the data has already been, substantially pre-processed and neatly organized.
Okay.
Attention as an inductive bias performs best when it's applied to data that's already, let's say, pre-compressed and at the right level of abstraction.
Yeah.
Think about it. In pretty much all real-world deep learning pipelines using Transformers, the raw, often messy data goes through some crucial encoding step before it hits the model.
And we've definitely seen examples throughout the series. Patchification in vision-breaking images into smaller patches. Right. And the big one for language. Tokenization. Converting text into these discrete, often subword units.
Precisely. The core idea is that the inductive bias of soft attention, allowing the model to dynamically weigh different input parts, is fundamentally geared towards what you might call hard attention, meaning it works best when each individual token it focuses on is already semantically meaningful, like how we read.
Yep.
We attend to words or subwords because they carry meaning immediately.
Right.
But attention really struggles at, say, the character level. Why? Because individual characters often lack that immediate high-level semantic weight. This can lead to real confusion from distractors when you're processing very high-resolution or fine-grained data. The signal-to-noise ratio at that lowest level can be tough for attention.
That makes sense.
In fact, there's some preliminary evidence, still needs more rigorous checking, mind you, but it hypothesizes that SSMs might actually be less prone to hallucination than Transformers, partly because of this difference in inductive bias.
That's a fascinating potential side effect. So, okay, if Transformers thrive on pre-processed high-level abstractions, where do SSMs, these brains, really come into their own? Where do they show their unique advantages?
Well, SSMs demonstrate a clear and sometimes really surprising advantage when the data is high resolution, inherently noisy, or just lacks those immediate, obvious semantic units for attention to easily grab onto.
Right.
We've seen this consistently with character-level language modeling or even complex sequences like DNA, places where traditional attention models tend to struggle quite a bit.
Right.
SSMs with their compressed, continuous internal states are just inherently suited to taking this raw, high-res, often undifferentiated data and progressively compressing it to more meaningful, higher-level abstractions.
So it's not just about being more efficient computationally?
No, though they are efficient. It's about a fundamental difference in modeling power for these specific kinds of data. For instance, look at the empirical results. On untokenized language, raw bytes or characters, SSMs seriously outperform Transformers, often even when the Transformer gets way more compute.
Okay, that's significant.
Yeah, and this is a really critical insight on the same. Tokenized data, their perplexity curves are often very similar, or sometimes the Transformer might even be slightly better. This highlights something profound. Just untokenizing the input lets the Transformer use much more compute because the sequence gets longer. But paradoxically, its relative performance decreases compared to the SSM.
Wow. That really makes you question the standard approach, doesn't it?
It absolutely does. It raises crucial questions about how we've typically handled data pre-processing and the inherent biases baked into our go-to architectural choices. Maybe we've been optimizing for an abstraction that isn't always the best one.
That observation about untokenized versus tokenized data really makes you pause. It feels like it leads directly into this broader philosophical point in deep learning, the one often called the bitter lesson. It almost feels like a guiding principle for AI progress.
It really does. The bitter lesson, yeah. It's this concept arguing that the major leaps forward in AI haven't come from clever human feature engineering, but consistently from replacing that handcrafted stuff with powerful end-to-end neural networks. Models that just learn patterns automatically from raw data, given enough compute.
Like the shift from manual edge detectors in vision to CNNs learning from pixels?
Exactly. Or in NLP, moving from linguistic features, part of speech tags, parse trees, to transformers learning directly from raw text.
Right.
And removing tokenization. It fits right into that spirit. It's not just about the practical pluses like fixing edge cases or making model comparisons easier.
Well, those are nice too.
They are, but it's about a more fundamental shift. Letting models automatically learn the basic units of meaning directly from the raw data, without humans imposing segmentation first, which is exactly what HNets are aiming to do, embody this principle of less human data meddling, more automatic end-to-end learning.
Learning hierarchical abstractions from raw data.
Okay, so if tokenization is potentially this bottleneck, this piece of handcrafted engineering we want to move past, how do we actually do that? This seems to be where HNets really come into play, offering a path towards that end-to-end vision.
Precisely. The core idea driving HNets comes from this deep appreciation for hierarchy, which, if you stop and think about it, is just everywhere in how we process information, how we structure the world.
Right, sounds build into phonemes, phonemes into words, words into sentences.
Exactly. That nested structure is fundamental. So the goal with HNets was to develop a core computational primitive for chunking, a simple differentiable building block that could learn, dynamically, how to organize raw, high-resolution data into more meaningful higher-level units.
Moving beyond fixed, predefined tokens.
Definitely. Aiming for a more appropriate, adaptive way to model language and potentially other kinds of sequential data, too.
That focus on hierarchy and dynamic chunking, it definitely rings a bell. Makes me think back to some earlier attempts like, wasn't there the clockwork RNN or ordered neuron LSTMs? Are HNets building on that kind of legacy? And what's the key innovation this time?
You're absolutely right to make that connection. HNets definitely build on that rich history, but with a really critical distinguishing innovation, this data-dependent dynamic chunking or DC mechanism. And the key is that it learns the segmentation end-to-end jointly with the model's main task.
Okay, so not using external rules.
Right. That's unlike prior attempts, like
Yeah.
SpaceByte or the byte-latent transformer. They often relied on external heuristic rules, predefined delimiters, maybe conditional entropy thresholds calculated by a separate pre-trained model, and even things like the dynamic pooling transformer, which tried an end-to-end approach, apparently struggled quite a bit with training stability. That really prevented it from scaling effectively to multiple hierarchical stages.
So HNets figured out how to make that end-to-end learning stable and scalable.
That's the goal. They're meticulously designed to learn these dynamic boundaries directly within the model and in a way that works reliably. B, how HNets dynamically chunk.
Okay, so given this end-to-end learning, how does an HNet actually decide where to draw these dynamic chunk boundaries? What's the principle behind that decision?
So the dynamic chunking mechanism itself has two main parts. There's a routing module that predicts where the boundaries should go, and a smoothing module that handles the decompression back to the original resolution later.
Okay.
The routing module operates on something we could intuitively call an uncertainty principle. Basically, it tends to draw boundaries when it gets surprised by the next token in the sequence.
Surprised? How do you measure surprise?
It's measured very precisely by the information content or the negative log likelihood of that next token.
Ah, okay. Not just conditional entropy.
Right, and that's a crucial distinction. Conditional entropy wouldn't necessarily signal true surprise if, say, a very rare but still kind of predictable word popped up in a low entropy spot. But negative log likelihood really captures the intrinsic information content of each incoming element. It signals when something genuinely unexpected or informative happens.
So it's like the model reacts to real information spikes, not just sequence predictability. It's like it's saying, whoa, this is new information. This is where a significant gain happened.
Yeah.
That's a really neat way to define a boundary. Does that maybe imply HNets might be more robust to noise or unexpected stuff because they're tuned to information density?
That's an excellent point, and yeah, the empirical results seem to support that idea. While the exact mechanics of boundary choice are still, an active area of research and refinement.
Yeah.
This connection to surprise or uncertainty has been pretty consistently observed. The ultimate goal is for the model to automatically discover these semantically coherent units just from the raw data, mirroring how older methods like SpaceByte validated their delimiter-based chunking for English and code, but now doing it completely end-to-end.
And how does this dynamic chunking, which sounds pretty intricate, fit into the overall HNet structure? Is it separate or deeply integrated? And crucially, where do SSMs like Mamba 2 fit in?
Okay, so HNets use a hierarchical UNet-like architecture. Think like image processing networks handling different levels of detail.
Got it.
And importantly, the encoder and decoder networks, the parts that interface directly with this dynamic chunking mechanism, they are strongly improved by using SSMs, specifically Mamba 2 layers.
Ah, okay. How so?
Well, the encoder's job is basically to compress the raw inputs, bytes, pixels, audio samples, whatever, into these richer, more abstract chunk representations. And the decoder does the reverse. Decompresses these abstract chunks back to the original fine-grained resolution while
Huh.
trying very hard to preserve all that fine-grained information that got abstracted away.
Makes perfect sense. So why Mamba 2 specifically for those roles? What makes SSMs the right tool for the job there, especially dealing with that raw, uncompressed data at the bottom level?
It really comes down to their fundamental inductive bias. SSMs just have this strong inherent bias towards compression. They excel at processing fine-grained, continuous, or uncompressed sequences.
Okay.
This makes them perfectly suited for the encoder's job, taking raw stuff and efficiently compressing it into richer chunk representations. And similarly for the decoder, taking those abstract chunks and decompressing them back into detailed outputs while preserving information. SSMs are exceptionally good at that.
So the ablation studies confirmed this?
Emphatically, yes. Systematically swapping components showed that SSM-based encoders and decoders significantly outperform traditional transformer layers in these specific roles, even when operating on coarser, higher-level inputs later in the network.
Why even then?
It seems due to their superior compression capabilities generally, which are just invaluable for building these hierarchical abstractions effectively. So basically, any part of the model that needs to directly touch byte-level data or compress information into the next hierarchical stage really benefits massively from the unique strengths of SSM layers. See beyond tokenization, HNet's impact.
That's a really compelling case for their architectural fit. But, okay, what about the tangible real-world benefits? Are HNets actually delivering on this promise of moving beyond tokenization? What does that mean practically?
Yeah, the results we're seeing are quite compelling. They really underscore the potential here. For instance, just a single-stage byte-level HNet already surpasses the performance of standard tokenized language models, measured in bits per byte.
Bits per byte. Remind us why that's important.
Right, so bits per byte is a key measure of compression efficiency. It tells you how many bits of information are needed, on average, to encode each byte of the original data. Lower is better. It means the model has learned a more compact, efficient representation.
So matching or beating tokenized models is a big deal.
It's a potential game changer, yeah, because it suggests we can get similar or maybe even better performance without that costly, often problematic pre-tokenization step. Practically, that could mean lower data prep costs, maybe more compact models, since the model handles abstraction itself.
And potentially more accurate results because you're not losing information in a fixed tokenization scheme.
Exactly. Plus, HNets show really remarkable robustness to textual perturbations, noise, style changes, even simple typos things that can often trip up tokenizer-based models pretty badly.
Okay, that's huge for real-world use.
It's crucial, yeah. It points towards more integrated, less brittle AI systems that can tolerate messy real-world data better. For example, on benchmarks like HelloSwag that include these kinds of perturbations, a two-stage HNet showed substantially improved robustness compared to baselines trained only on clean data. It's learning to cope with unpredictability.
And what about areas where tokenization is already tricky, like certain languages or completely different modalities like audio or DNA?
Yeah, HNet's improvements seem even more pronounced there. In languages like Chinese, where word boundaries aren't always clear or encode with its specific syntax, HNets show significant gains. We're also seeing substantial improvements in DNA language modeling. One result showed a 3.6x improvement in data efficiency compared to standard isotropic models.
Wow.
And the key thing is, the model learns these semantically coherent units purely through end-to-end training. It's not relying on predefined rules. This really validates the approach's ability to find deep structural patterns that we used to impose by hand.
So the bigger picture.
The bigger picture is HNet's promise not just better long context abilities because of their hierarchy, but also a viable path toward truly multimodal models. Models that operate directly on raw data from diverse sources. That makes them a really strong candidate for the backbone of future general foundation models. 3. The power of hybrid models. Synergistic strength.
Okay, we've spent a lot of time talking about the distinct strengths of SSMs and transformers, almost setting them up as rivals. But is the future really about choosing one or the other? Or is there a path to bring them together, leverage their unique advantages synergistically?
That's a really important question. And the answer, based on some really exciting recent work, points emphatically towards the power of hybrid models.
Okay.
We're increasingly seeing models that strategically combine Mamba layers with attention layers. Think models like Jamba, Zamba.
Mm.
They're demonstrating that these mixed architectures can actually outperform pure transformer or pure Mamba setups at significant scales.
Really? Like concrete examples?
Yeah, for instance, empirical validation showed a hybrid model, just a few attention blocks, mixed with many SSD blocks outperforming both a pure 64-block Mamba 2 model and a standard transformer plus baseline, even a strong baseline with lots of attention and MLP blocks. This was at 2.7 billion parameters, trained on 300 billion tokens.
So mixing them gave better results than either pure approach.
At that scale, yes. It strongly suggests that a carefully balanced integration can unlock capabilities that neither architecture achieves alone.
So it's not just about one being inherently better, but about recognizing and combining these complementary strengths, almost like the architectural version of the whole is greater than the sum of its parts.
Exactly. You've nailed the core idea. The strategy is to leverage the best of both worlds. Attention's amazing ability to form dense, global connections and operate efficiently on sets.
Right.
And SSM's efficiency, their superior compression, that strong inductive bias for sequential processing and long-range dependencies. By cleverly interleaving these primitives, these hybrids strike a powerful balance, using each component where it shines brightest.
Distilling transformer intelligence.
That's a compelling vision for building new models. But what about the huge investment we already have in existing large-scale transformers? How do we bridge that gap, especially when these pre-trained transformers hold so much learned knowledge? Seems like a waste to just discard them.
That's where Mohawk comes in. It's a multi-stage distillation framework, and it offers a really powerful practical answer to exactly that problem.
Okay, distillation, transferring knowledge.
Right. It provides a systematic way to transfer knowledge from these big, pre-trained transformers over to sub-quadratic models like Mamba 2, which are much more computationally efficient.
How does it work? Is it just matching the final output?
It's more sophisticated than that. The process involves aligning not just the final outputs, the logits, but crucially, also aligning the hidden states across different architectural components.
Okay, so trying to capture the internal reasoning too.
Exactly. It's a more sophisticated form of knowledge transfer, trying to impart the learned representations and internal processes of the big transformer onto the more efficient SSM. Goes beyond traditional distillation that often just matches the final predictions.
And does this actually work well in practice? Or is it still more theoretical?
Oh, it absolutely works in practice. Experiments have shown Mohawk's ability to successfully distill knowledge from models like, say, Phi 1.5, that smaller scale open source model from Microsoft, into a Phi Mamba architecture.
And the result?
It led to notable practical performance improvements. The more efficient Phi Mamba could achieve really strong results on downstream tasks. For instance, OHawk helped a Phi Mamba get an average score of 65.1 on some benchmarks, performing very competitively against other attention Mamba hybrids, but using significantly fewer attention layers and parameters overall.
Interesting.
And one key finding from that research reinforcing this idea of synergy is that uniformly interleaving Mamba 2 layers with attention layers in these hybrid models consistently yielded superior performance on downstream benchmarks.
So it wasn't just about distillation, but the hybrid structure itself was important.
Precisely. It aligns perfectly with what we see in other successful hybrids like Samba. It really reinforces the idea that strategic architectural mixing, not sticking purely to one type, is often the best path to state-of-the-art results right now.
Bidirectional SSMs through matrix mixers.
Okay, so beyond just combining them, can SSMs themselves be adapted for tasks that transformers have typically owned? I'm thinking particularly about things requiring bidirectional context, like non-causal masked language modeling. That's always been a key transformer advantage.
That is precisely where Hydra comes onto the scene. Hydra introduces a really significant innovation, a bidirectional extension of Mamba, specifically designed for those non-causal tasks.
Bidirectional SSMs, how does that work?
Right, so unlike standard causal models predicting only the next token, masked language modeling needs context from both left and right of a hidden word. Bidirectionality is essential.
Okay.
Hydra is parameterized as something called a quasi-separable matrix mixer. It's a powerful, pretty elegant mathematical concept. This framework gives a systematic way to develop sequence mixers with specific desired properties.
And what does that framework reveal?
It shows that these quasi-separable matrices actually generalize both low-rank and semi-separable matrices. And crucially, they can be efficiently decomposed into operations that include SSMs.
So how does Hydra get the bidirectionality?
Essentially, it cleverly decomposes the quasi-separable matrix multiplication into two semi-separable matrix multiplications. Then, using simple flip and shift operations, it allows information to flow in both directions across the sequence within that SSM-like structure.
Wow, okay, that sounds incredibly clever. What are the results? Does Hydra actually compete with or beat transformers in these domains like NLU or even vision?
The results are very impressive, yeah. Hydra has shown superior performance, acting basically as a drop-in replacement for attention layers in these contexts.
Examples.
It notably outperforms BERT, a foundational transformer for NLU, by about zero point 0.8 points on the GLUE benchmark.
GLUE, the Standard Language Understanding Benchmark Suite.
That's the one. A collection of diverse tasks testing semantic and syntactic understanding. And maybe even more strikingly, Hydra surpasses VIT, the vision transformer, by a significant 2% on ImageNet 1K image classification.
2% on ImageNet is huge, especially against a vision transformer.
It is. And what's really remarkable is that Hydra just flattens the image into a sequence of pixels. No special 2D architectural tweaks, none of the extra stuff common in vision-specific transformers.
That's amazing.
It really highlights the versatility and power of that underlying quasi-separable matrix mixer framework. It can handle diverse data types and tasks needing bidirectional context incredibly well. The fact that it overcomes such a performance gap, especially in vision without specific tweaks, really underscores how essential seamless bidirectional processing is for these demanding tasks. 4. Overcoming engineering challenges.
Yeah.
Making the future practical.
Okay, these dynamic and hierarchical architectures, especially HNets with all their interacting parts, sound incredibly powerful on paper. But they also sound, frankly, inherently complex to actually build, debug, optimize. What are the real-world engineering challenges in bringing these ideas to life, making them practical?
You're absolutely right to point that out. They definitely introduce a significant amount of complexity, lots of, moving parts that all need to mesh perfectly.
Yeah.
For instance, with HNets, getting all those critical axes of variation, the routing versus smoothing, how info aggregates across hierarchy levels, getting them to interact in exactly the right way. The researchers described it as one of the most difficult empirical projects they'd undertaken.
Wow.
It involved countless iterations, months of painstaking hyperparameter tuning, fundamental algorithmic tweaks just to get stability and optimal performance.
So not trivial.
Not at all.
Mm-hmm.
However, and this is crucial, we need to see these not as impossible barriers, but as surmountable challenges, much like the development cycles we saw for other complex, powerful architectures. Think mixture of experts models, MOE.
Right, those took a lot of engineering effort too.
Exactly. Or even advancements like speculative decoding.
So the path is similar to past breakthroughs, requiring this continuous, almost artistic process of discovery and refinement. Sounds like a lot of trial and error, not just pure math.
Precisely. Every major architectural leap in deep learning has faced its own unique set of empirical hurdles to achieve stability and competitive performance at scale. It really is an art as much as a science. It needs deep intuition, perseverance to get all the components humming together seamlessly. The effort involved in getting dynamic chunking robust end-to-end, for example, really highlights that iterative process.
Yeah.
It's not easy, but the potential payoff generalizable robust AI is huge.
And thinking about scale, how do these new architectures handle the massive parallelism needed for training today's biggest models across many GPUs?
Yeah, that's critical. Both transformers and SSMs are evolving here. For transformer-like models, we have techniques like ring attention, enabling sequence parallelism, splitting the sequence itself across devices.
Right.
For Mamba 2, the structured state space duality SSD framework is the real game changer. It provides this brilliant block decomposition. Each GPU computes its local output and final state independently. Then those states are efficiently passed between devices using optimized communication links. This fundamentally enables efficient context parallelism, letting Mamba 2 models scale to incredibly long sequences across many devices.
And what about variable sequence lengths? That's super common in real-world inference. Transformers often need padding or complex load balancing.
Right, which wastes compute or adds complexity. This is another area where SSMs offer a remarkably clean, elegant solution.
How so?
Unlike transformers needing padding or complex balancing, SSMs can basically just treat an entire batch of sequences, even with different lengths, as one long concatenated sequence.
Okay. But how do they keep the states separate?
They cleverly avoid state transitions between the individual sequences within that batch. They do it by strategically setting the state matrix to 0 for the tokens that fall at the very end of each sequence.
Ah, like a reset signal.
Exactly. It's an ingenious method that dramatically simplifies handling variable lengths without sacrificing efficiency. No complex brittle load balancing needed in inference. Much more practical.
You mentioned the tuning difficulty and stability for these complex models earlier. How are researchers addressing that, ensuring robust training with all these dynamic parts?
Well, for agents specifically, introducing that smoothing module and the similarity-based routing module turned out to be absolutely crucial.
For stability.
Yes, essential for maintaining stable gradient flow during training and also for getting interpretable, consistent chunking boundaries. Without them, the models could become severely unstable, just unable to learn consistent patterns.
Okay.
And interestingly speaking, again, to the power of hybrids, sometimes incorporating a few transformer layers into the main HNet network, especially near those dynamic chunking modules, can actually alleviate instabilities that were sometimes seen in pure Mamba 2 only setups.
Even though Mamba generally performs well.
Yeah, despite Mamba's strong general performance, it suggests that even within these novel architectures, a carefully chosen bit of hybrid design can really help with stability.
So it really is this constant iterative process, empirical discovery, refinement, subtle design choices having huge impacts on practicality.
Absolutely. It's an art and a science. Deep intuition, tons of experimentation to get everything interacting robustly. And, the significant speed up of Mamba 2's SSD algorithm over Mamba 1's selective scan, especially at larger state sizes, that also speaks volumes. These ongoing system-level optimizations, often finding clever ways to use modern hardware like matrix or multiplication units, that's what turns a theoretical breakthrough into something practical, efficient, and actually deployable. V, the integrated AI landscape, future outlook, and open questions.
Okay, looking ahead now, beyond these immediate advancements, what's the ultimate vision here? What kind of AI systems are we really trying to build with these new tools? What does it mean for the broader field?
Well, the driving vision, fundamentally, is creating more integrated, less brittle AI systems.
Less brittle,
Meaning a profound shift towards models that can truly learn directly from raw data, bypassing traditional, often handcrafted, pre-processing like tokenization or image patching. The goal is for them to operate naturally, robustly over dynamically learned abstractions, much like our own brains seem to do.
Right.
HNets, for example, really embody this. They aim to become the foundational backbone for truly general foundation models, capable of processing pretty much any raw data stream you throw at them.
And this aligns with the bitter lesson again.
Deeply. Every major advance seems to involve removing human-engineered features, favoring automatic end-to-end learning.
It sounds like this grand pursuit of finding truly universal primitives for how AI processes information, reducing human intervention in data prep, letting the AI find its own representations.
Indeed. You can think of the work on SSMs and attention as fleshing out these fundamental computational primitives. SSMs define recurrence and continuous time processing. Attention defines dense connections or functions on sets for global interaction. Now, chunking emerges as another potentially crucial fundamental primitive, aimed at dynamically organizing raw data into meaningful context-dependent units. These primitives are like the basic building blocks, capturing fundamental ways to transform information, designed to be flexible, scalable across diverse tasks and modalities, driving us towards more generalized intelligence.
That's incredibly exciting. But, with every new frontier, there are always fascinating, unresolved questions. What are some of those critical open research questions that these advancements bring up? Where are researchers focused next?
Well, one really important question is further formalizing what actually constitutes the right level of abstraction for data processing. It's still a bit fuzzy, intuitive,
Right.
but it's absolutely critical for optimal model design for peak performance, finding that sweet spot, efficient processing without losing crucial detail or getting bogged down in noise. Another really intriguing area is the potential connection between SSMs and actual biological nervous systems. Given Hippio's origins in optimal online compression and memory, a very biologically plausible problem, there's a fascinating path to explore how these math models might mirror or even inform our understanding of natural intelligence. Could open up whole new interdisciplinary avenues.
And how do we rigorously test these theoretical ideas, these intuitions about ideal architectures, beyond just looking at perplexity or accuracy scores?
Absolutely. Thought experiments are powerful guides here, like the litmus test proposed for an ideal architecture.
The litmus test.
Yeah, it posits that an ideal model should be able to process a sequence containing significant noise or redundant fillers without substantially increasing its compute or memory needs. Essentially, it should behave almost identically on data sets with the same core information content, regardless of the surrounding fluff.
Has that been tested?
Well, it's a guiding principle, not fully empirically verified for all aspects of HNETs yet. But these thought experiments really help shape architectural design. For instance, S4's remarkable ability to adapt to different sampling rates just by changing an internal step size without retraining. That's a powerful example of moving towards that kind of robustness and efficiency, especially with varying information density.
So this definitely isn't the end of the story for sequence modeling. It feels much more like a profound new beginning, with new frontiers opening up incredibly fast.
Without a doubt, the field is evolving at a really rapid pace. We've seen how even simplified diagonal SSMs like S4D can closely approximate the complex dynamics of the original DPLR S4 models,
Mm.
often performing similarly on benchmarks. Simpler can still be powerful.
Right.
The ongoing exploration of timescale parameters and SSMs, how they relate to the continuous processes being modeled versus the discrete data we feed them, that remains a rich research area. Different settings seem optimal for different tasks, different data types.
And the future.
And the continued development of hybrid models, the elegant distillation of knowledge across architectures, maybe even more sophisticated dynamic hierarchical structures. All this will undeniably lead to even more efficient, more capable, and ultimately more universally intelligent AI systems. The ability to move towards truly end-to-end learning from raw data, operating over learned abstractions. That marks a monumental shift in how we build and how we fundamentally understand intelligent systems.
What an incredible journey it's been, exploring this exciting new frontier beyond Transformers, from, the brain-like efficiency and maybe infinite memory of SSMs to the raw data power and end-to-end learning of HNETs and that synergistic promise of hybrid models. It's just abundantly clear the landscape of AI is continually shifting, integrating, pushing the boundaries.
And the key takeaway for you, our listener, is probably that this rapid progress isn't just about squeezing out more speed or building bigger models. It's really about pushing towards more fundamental principles of learning, designing models that are less brittle, more adaptive, and ultimately maybe more aligned with how intelligence could truly emerge from complex, noisy data, moving beyond the limitations of handcrafted preprocessing.
So, as you reflect on this deep dive, maybe consider this provocative thought. If AI systems can genuinely learn to process raw, untokenized data and dynamically chunk it into meaningful hierarchical abstractions all on their own without human guidance,
Hmm.
how might that fundamentally change the way we interact with, create, and even define information itself in this digital age? It really feels like it opens up a whole new paradigm for how we approach building intelligence, one where maybe the machines start to truly understand the world on their own terms. Thank you for joining us on this deep dive into the future of sequence modeling.